All right, and welcome back to another LeetCode easy problem. If you've watched some of the videos, you might already know that I'm actually a fan of doing easy problems because they help you to practice the interview process because they don't distract you as much with making it difficult to solve the problem. So you can really focus on your communication, writing clean code, explaining your ideas, explaining your runtime and space complexity trade-offs when you choose one implementation or one approach over the other. So today we're going to look at LeetCode 3330, find the original typed string number 1. So I suppose there's a series of problems like this. I have not solved this problem myself, and I have also not looked at this before. So yeah, so you get, I guess, you will have a first look together with me at this. So the first thing to do is always read the problem description. The second thing, check the constraint. The third thing is check out the examples. And then we will hopefully have an idea of how we can solve the problem. And if we are lucky, we can already give runtime and space analysis before we write the first line of code. If the problem lends itself to it, there might even be different approaches that we could explain before we start writing code. And then we'll eventually write code, implement it, and step through it in our mental debugger before we hit the run button for the first time. So that's kind of the TLDR of how to break down these problems systematically. And yeah, and it's okay to make mistakes at any of those stages, but the structured approach gives you an opportunity to recover. And nothing is worse in an interview than just being silent and nobody knows what you're doing. So anyways, I'm rambling, so let's get into it. Problem description. Alice is attempting to type a specific string on her computer. However, she tends to be clumsy and may press a key for too long, resulting in a character being typed multiple times. Although Alice tried to focus on her typing, she's aware that she may still have done this at most once. Okay, so at most once in the entire string, or I guess so. Not okay, I suppose so. You are given a string word which represents the final output displays on Alice's screen. Return the total number of possible original strings that Alice might have intended to type. All right. Okay, so we're getting a word that has at least one character in it. You know, the edge cases are always important, so at least one, that's good. And the word consists of only lowercase English letters. Nice. Example 1. Word input A, B, B, and then 4 times C. Output 5. Return the total number of possible original strings Alice might have intended to type. Okay, so why 5? The possible strings are A, B, B, and all the C's. So the original string is actually one of the possibilities. Okay, so we assume Alice didn't do any typing mistakes. Another one is where we type the original string but one less C in the repetition, then 2 less C's, and then only 1 C. And the other example is where Alice typed the B twice by pressing the key too long. Okay, so now it becomes clear. So she is aware that she must still have done this at most once. So that means that if we see repetitive characters in the string, only one of these characters might have been, well, only in one of these instances might Alice have pressed the key for too long. So it can't be that Alice pressed the B key too long and the C key. It's either or, right? That is why here we have AB followed by the 4 C's, but we don't have any variations of that where we have AB and 2 C's. For example, because if you have A, B, and 2 C's or 3 C's, that would mean that Alice pressed the key too long on the B and on the C. Now, this example also tells me that if there are any character repetitions, there is a potential key press where Alice pressed too long. Right, so we're not dealing actually with dictionary words or anything like that. We're really just looking at the characters and if they repeat. Okay, let's see if what we've concluded so far is true, and by looking at example 2. Okay, all the characters are different. There are no repetitions, so the number of different possible original strings that Alice might have typed is exactly 1, because that's the only one we have. We don't see any variations that could have been possible due to the absence of any repeating characters. Right, and now the word AAA. So here I suppose one would, well, because we know the minimum word length is 1, right? Alice never types the empty string. So it's AA is the second word, 3 A's is the third word, and 4 is the fourth word. So that's why the output is 4. Okay, cool. So I think it is clear that we have to, so we're discussing now solution approaches. I think it is clear that Alice has, well, we have to iterate through all of the characters and identify repetitions, right? And so we will have runtime complexity that is linear dependent on the number of characters in the string, right? Time. And I also think that we can actually update our final output while we do this iterating over of the characters, so that we really just need to store that number, and which would be of 1 space, so constant space, where n is just the length of the word. So what I would do is, let's just iterate over all of the characters. And every time we see a character that is the same as the previous character, we have to increase our output counter. So if we, for example, if we go through this example string, we have the character A, the character B, no repetition so far. Now we run into the character B for the second time. So we have a repetition, and we need to increase our counter from 0 to 1. Actually, I think we should start with a count of 1, because the entire word is one possible way that Alice could have typed the word. So let's find a good name real quick. Number of possible strings. I'm just call this counter. We're going to return at the end. So for character in word, and we're going to have a reference. Well, actually, we're going to iterate with an index over the word. For I in range, length word. We're going to start at index 1, so that we can say the previous character is word I minus 1, and the current character is word at position I. Right, and then we do the check. If previous equal to current, then we would increase our counter by 1. So that is what I just explained, put into code. But now let's finish our example here. So if we have, let's step through this code with this example to see, because I don't know if this works, but I think it will, but I have to check now. So first we check if A and B, previous is A, current is B, no repetition. Then we check BB, they're the same, so increase our counter by 1. Next is, we have BC, so they're different again, we don't increase our counter. Just to remember, our counter is currently at value 2. We incremented it only once, so that's 2 right now. Next, we run into the first CC, so we increase our counter from 2 to 3. Then we have, again, the case where we have 2 repeating Cs as in previous and current. So now we increase our counter to 4. And then finally, we have the final repeating Cs, and we increase our counter to 5. So in this example, it works. And if we have no characters that are repeating, we we will never have execute this if statement, but we'll have the origin count of 1, which we will return. Just to be, well, in an interview, I would be confident now to say, okay, I think this is a solution. But to be sure, let's just step through the third example as well. So we have 4 A's. We start with a count of 1. Remember, we compare now these two. That means they're the same. We have to increase counter to 2. Then we encounter these. So it goes to 3. And then we have the last, and then it goes to 4. So yeah, I'm fairly confident that this is a good approach. If somebody asks me, is there a better runtime algorithm out there for that? I would say, unless we can exploit some structure about the word string, we probably won't be able to, because we have to look at all characters and their predecessors in order to determine that. Right. Well, actually, yeah, we do have, because the not only the count of the character matters, but also the position. So if we had a string that starts with 4 C's and then some B's and then another 4 C's, it doesn't mean that we have 8 repeating C's in it. So the position also matters. So that's why we have to iterate through them. That's how I would reason. Although that's not scientific, but like, I guess, explaining my intuition behind that. Okay, so the test case is passed, and the test case is always the same as in the example. So now let's be brave and submit this code to be judged by the LeetCode. And there you have it. So nice. And by the way, if you ever wonder whether runtime memory matters, no, it doesn't. If I submit this code a couple of different times, or different times of the day, I get different runtimes. So 23 milliseconds, now it's 31 milliseconds when I run it again. So this is completely irrelevant if you're preparing for interviews. What matters is the asymptotic runtime and space complexity. And also, and I've said this before in meetings, on LeetCode, there are always constraints on the size of the input. So technically speaking, everything is O of 1, right? Because it has a fixed upper bound. But in an interview, you assume that, okay, the word could be like arbitrary length, even if that's not realistic on to be run on a computer. LeetCode has these constraints so that that they can execute the code and test your code, right? Yeah. Let's have a quick look at maybe the solutions. Maybe find something interesting there as well. Something that we could try to re-implement. Counting principle, add and subtracts. Python one-liner. That's interesting. Although I would never write a one-liner in Python. Okay, some math. Nobody wants to deal with that stuff. Complexity, but this is C++. I don't know. It's not really worth my time to look at C++ implementation. So this guy lied. I clicked Python and gave me C++. Super easy for beginners. 4 lines of code. There are the number of lines. You're not going to be judged for that in an interview. Maybe if you do like, what is called? Golf coding or coding golf or whatever. And easiest Python solution. All right, let's have a look at that. This one uses exactly the same principle, but it makes it more complicated by adding another if statement. Does the exact same comparisons that we do here, but it's less explicit, right? Previous and current. Good variable naming goes a long way. So if your code is easy to understand, that's better than, I could just do this, right? Yeah, but this is easier to understand. And in an interview, you want to communicate stuff. And you can always excuse what you're writing by saying, I just want to make it very explicit. You could say in production code, I would maybe do it slightly different. What else do we have? Or a more voting algorithm, O of 1. So this one doesn't really improve our time complexity. What is this person doing? So this one is keeping a previous variable, so it goes over all of the characters in the word. I don't know why it used the variable name let. I would never do that. Previous is fine. I would rename this to current. Then it's exactly the same thing that we have. I don't know, really? Pretty almost similar. Well, almost can be far away off. So yeah, I don't think there are any interesting solutions here, but maybe there are, but I'm not going to look any further. So that concludes LeetCode 3330.